You pull out your phone on a busy Delhi street, tap a link for Wikipedia, and the page loads in a fraction of a second. The entire process takes anywhere from 50 to 500 milliseconds. Because this happens wirelessly, we rely on terms like Wi-Fi or the cloud, and we often assume this invisible data is beaming down from satellites in space. But satellites actually handle less than 1% of global internet traffic. Space has very little to do with your daily browsing. The internet is an intensely physical infrastructure. It is a sprawling global machine built from thousands of miles of copper, glass, and heavily air-conditioned data centers. To see how this machine actually operates, we need to freeze time the exact moment you tap that screen and track the physical journey of your click across the globe. Tracing this route reveals the internet's true identity, a vast physical machine built from concrete components that we interact with every single second. Your browser cannot read the name Wikipedia. Computers require numerical coordinates, known as IP addresses, to locate a destination. Your phone contacts a DNS server, the internet's phone book, trading the web address for an IP address like 208.80.x.x. The request then goes to your local internet service provider, passes through an exchange point, and hits a Tier 1 global backbone network for international transit. This local routing is the on-ramp. It bridges the small wireless hop in your living room to the massive physical arteries connecting continents. Your request leaves India from the coast of Mumbai and plunges underwater, entering a submarine fiber optic cable laid by ships exactly like this one. Down here, your data becomes pulses of laser light. It races through glass cores on the ocean floor at 200,000 kilometers per second. This map shows the scale of these underwater routes. There are over 1.5 million kilometers of active submarine cables kindly connecting the continents. Because 99% of international internet traffic flows through these fibers, the global exchange of information rests in the freezing depths of the world's oceans. Those light pulses eventually reach land and arrive at a hyperscale data center in Europe or the US, where the Wikipedia servers prepare to send your web page back. Sending a 6-megabyte web page as one file causes a massive traffic jam. Instead, the TCP protocol chops the page into numbered packets. Routers then act as traffic cops, sending these packets down completely different global paths to avoid congestion. Chopping data into independent packets creates resilience. If one fiber cable gets cut by a ship's anchor, the routers instantly send the remaining packets on a detour. The delivery is guaranteed. Having navigated multiple paths across the globe, those scattered packets pour out of your local cell tower and back into your phone. Using those TCP sequence numbers, your browser instantly sorts the packets into order and perfectly renders the HTML, CSS, and images into a seamless web page. We can unfreeze time now. From the exact moment your finger tapped the glass to the page appearing, only 250 milliseconds actually passed. Looking at this diagram of network nodes, you can see the true scale of the system. This exact millisecond-long journey is happening right now for 5.7 billion users, moving over 400 million terabytes of data every single day. The system is composed of more than 75,000 independently operated networks, known as autonomous systems. They belong to fiercely competing companies, yet they trade traffic and cooperate flawlessly using shared rules. No single entity owns it. The internet operates as a decentralized global symphony. Every click is the physical activation of 75,000 competing networks cooperating through a single set of shared rules.